I welcome everyone in today's session where we will go through the basics of reinforcement learning. We will go through the basics of reinforcement learning. Throughout this session, what we are going to cover is, we'll go through the basic definition of what is reinforcement learning. Subsequently, we will get familiar with the terminologies, what people use in the domain of reinforcement learning. Then we'll look at the key features of reinforcement learning, various elements, and there are several approaches to implement reinforcement learning. We'll look into that also. And how does reinforcement learning work? We'll look into that one also. The Bellman equation, how it helps us to calculate the values and how we make the decision for choosing our actions. That we'll take a look at also. Reinforcement learning algorithms, we'll take a look at few algorithms which people use. MDP, Markov decision process, we'll go through quickly, and we'll also take a look at what is Q-learning. And finally, we will try to understand what are the differences between supervised learning and reinforcement learning. What are the differences between supervised learning and reinforcement learning, and what are the applications of that, and then we'll finally conclude the session. Right? So that's the session plan. Let's begin with the basics of reinforcement learning. So, reinforcement learning is nothing but a feedback-based machine learning method. Where we have an agent which learns to behave in the environment by performing the actions and seeing the rewards or results of those actions. So let's say we have an agent, right, and it has to act in a particular environment. So it looks at the situation and takes certain actions, and what are the rewards or penalties of those actions. It will understand, and based on that, for each good action, he gets a positive feedback, which he will continue in future. And for each negative or bad action or suboptimal action, he'll get a negative feedback or a penalty. Right? So if I take a correct action to solve a particular task or situation, I get the positive reward. And if I haven't taken a right action, I may get a penalty. I may be penalized. Therefore, agent will learn based on the reward system or penalty system, what it is receiving after the action. Now, in reinforcement learning, that agent learns automatically by looking at those feedbacks without any labeled data. Which is unlike such as in supervised learning, such as we have seen in supervised learning. Since there is no labeled data, agent is bound to learn by the experiences. Agent is at its own. It has to walk through the environment, after trial and error method, it has to take an action, look at the reward or penalty. If the reward is high, continue that action, else change the action and learn. This is how the reinforcement learning works. Now, reinforcement learning solves a specific type of problem where decision making is sequential. And the goal is long term, right? Such as, let's say, I have to learn, change the action, and reach the final goal, which is generally going to be a long-term event. Such as, let's say, we can apply in game playing or robotics or several other fields where we apply the reinforcement learning. The agent will interact with the environment and it explores by its own experiences. Agent will interact with the environment and it will explore by its own experiences, and the primary goal of the agent in this particular reinforcement learning method is to improve the performance by maximizing the rewards, and minimizing the penalties during its actions, right? So this is the major goal of the reinforcement learning. Now, when agent interacts or when it is in the field, it will try to learn the entire process or the events by hit and trial method. So based on the experiences, it will learn and perform the task. So it will try, learn and perform. And it will try to minimize the penalties, maximize the rewards. Hence, we can say that this reinforcement learning is a type of machine learning method where any intelligent agent that will interact with the environment and learn to act within that particular situation based on the experiences. Learn to act within that situation based on the particular experience, right? And it is a core part of artificial intelligence. If you look at this, it is very nearer to artificial intelligence because it works on the AI generally works on the concept of reinforcement learning, because that agent or the model has to evolve at its own by learning and keep changing it, right? So it has to learn from its own experiences without human intervention, right? Without humans' input, it has to develop its learning at its own. Like, let's say, suppose there is an AI agent which is present in a particular maze environment, and the goal is to find out a particular diamond, right? It has to search a diamond, and we'll take a look at that problem statement. And agent has to interact with the environment by performing some sort of actions, and based on those actions, the state of that particular agent will be changed, and also it will receive a reward if the state change is in the right direction to receive a diamond, or it may get a penalty or feedback if it is not in a right direction through which he gets that diamond, right? So that was one example. So let's say the agent will continuously do certain tasks. Let's say it will take a particular action, change the state, remain in that state for a while, and then take the feedback. If the feedback is good, continue. If the feedback is negative, or if that's a penalty, change the action, right? And by doing these actions, it will learn to explore the environment. By doing these actions, it will learn to explore the environment, and that agent learns that what action leads to the positive feedback and which action has given the negative feedback or penalty, and according to that it will learn. So if there is a positive reward, agent will continue that, and if there is a penalty, agent will change its action. Let's go through some of the terminologies which we frequently use in reinforcement learning. Such as, let's say, here agent is nothing but an entity which can perceive or explore the environment and act upon it. So that is majorly our target entity which goes into the environment and explore. Environment is nothing but a simulation or a particular situation in which that agent is present or surrounded by. Right? In reinforcement learning, we basically assume that it's a stochastic environment, and which means it's totally random in nature, right? It has to try and see the reward, try and observe the reward. And action, those actions, they are nothing but, those are the moves taken by that agent in that particular environment to accomplish a particular goal. And reward is nothing but a feedback return to the agent through the environment or from the environment after taking a particular action as an evaluation, right? It could be a reward or it could be a penalty also if the action is incorrect. The policy is known as a strategy which is applied by the agent for the next action based on the current state. So let's say if I have taken a particular action, I got the positive feedback. The policy is to continue with those kind of actions. And let's say if we got the negative feedback or a penalty, the policy is to change that such that the penalty is minimized. Value, it is nothing but the expected long-term return with the discount factor, and it is opposite to the short-term reward definitely. So based on that value function, we keep changing our actions to accomplish a long-term goal. Q value is mostly similar to the value, but it takes one additional parameter such as, let's say, current action. We'll take a look at those also. Now, let's see the key features of reinforcement learning, where agent is not instructed about the environment and doesn't know in the advance that what actions have to be taken, and it is totally based on hit and trial process. It is totally based on hit and trial process or trial and error method. The agent takes the next action and change the state based on the feedback what it receives, right? And the agent may also get a delayed reward. So let's say sometimes you take the action, but the reward could be delayed. So we have to accommodate that also in our mind when we design the program. And the environment is nothing always stochastic, which is random in nature, and agent needs to explore to get the maximum positive reward, right? Maximum positive reward. Now there are certain approaches to implement reinforcement learning, such as, let's say, value-based implementation. The value-based approach is about finding an optimal value function which is maximum for a particular state under that policy, right? So that the reward could be maximized. Now, therefore, the agent expects a long-term return at any state under that particular policy. Let's say you can give a name to that policy. So we try to design a policy so that the reward is maximized and penalty is minimized. Now, the policy-based approach is to find out the optimal policy for the maximum future rewards without using the value function. So where we don't use the value function, here we use the value function, and based on the value function where the value is maximized, we take the action. Whereas in the policy, we don't use a value function, but we design a policy which is optimal in the direction of maximizing the reward, and agent will try to apply such a policy that the action performed in each step is that helps to maximize the future reward, right? And the policy could be based on the stochastic approach as well as deterministic approach. There could be another approach also, such as, let's say, model-based approach, in which a virtual model is created for a particular environment, and the agent explores that environment to learn, right? And there is no particular solution or algorithm for this approach, because we expect model representation, right? We expect that it should be, model will, it has to be explored at its own, and because of the model representation is different in each environment, right? So that's why this approach is called. Now, if you look at this, there are certain elements of reinforcement learning, such as, let's say, policy, reward signal, value function, model of the environment, right? So policy, which means we have fixed a policy which is optimal, and based on that policy, when we take the action, we get the maximal reward and minimum penalty. Reward signal is nothing but represents how much reward we get, and a value function generally used to compute the values of those rewards after a particular action which we have taken a look, and we will see in more detail. Model of the environment is nothing but that models the environment. Policy. A policy can be defined as a way how an agent behave at a given time. And it maps the perceived states of the environment to the action taken on those. It maps the perceived state of the environment to the action taking on the states, right? So now a policy is generally a core element of reinforcement learning. core element of the reinforcement learning. In some cases, it may be simple function or could be a lookup table also, where in some other cases, it may evolve a computation, a general computation as a search process, right? Now, let's say for an example, it could be deterministic, where you can say a particular action is taken based on a policy for a particular state, to accomplish a particular state, or it could be stochastic also, so where the action, they are dependent on the certain conditions, and then we take those. So using the conditional probabilities, we look into the stochastic direction also. Reward signal. The goal of the reinforcement learning is generally defined by the reward signal. At each state, the environment sends an immediate signal to the agent. Signal to the agent, and generally this is known as a reward signal. So let's say if I take a particular action and reach a particular state, my environment will send a signal to the agent to mentioning about the reward, right? So these rewards are given according to the good, or it could be a penalty also based on the action taken by a particular agent. So let's say a student, if he is preparing for the exam, and let's say if he is focused and nicely preparing, so that's the action, and the environment is, let's say, the results of the exam. Now, if he performs well, if he is focused, if he controls his emotions, save the time, learn in the direction of producing the outcome, and I assume that the learning is outcome based, and then the reward is naturally the positive grades. The positive grades. On the opposite side, it could be negative as a penalty if the time is not utilized or the study strategies is not optimal. Agent's main objective is to maximize the goal, right, or maximize the rewards, right, such as let's say a student's main objective is to maximize the grades. So accordingly they have to study. The reward signal can change the policy, such as let's say if the action is taken by the agent which leads to the lower reward, then policy may change to select another action in future, right? So it has to change to another action. If let's say if I'm not able to perform well in the exam, I have to change the strategy and try something new. The value function that gives information about the good situation and action, and how good the situation and action, and how much reward which we get. So that is a value function. Such as let's say a performance grades of a student could be a value function, and based on that quantified value function, we may take a decision that how much we want to study for the next exam, or how much we can change what is the variation in our strategy to accomplish larger grades. A reward indicates that an immediate signal for each good and bad action. Now I think this we have seen. So that model is generally known as, it mimics the behavior of the environment, right? So model, what is model here? It mimics the behavior of the environment. With the help of the model, one can make inferences about how the environment will behave, right? How the environment will behave. Such as let's say, if a state and actions are given, then what model can predict the next state and reward? So such as let's say here model could be exams, right? So that is the model, and based on that we can decide how to tune around for the preparation for the exams, right? So accordingly we can change our strategy and study pattern to increase the reward. The model is generally used for planning, which means it provides a way to take the course of actions by considering all future situations before actually it is experienced. So such as let's say we have been attending the exams in past, we have attended few exams. Based on those exams, we can understand and tune around our actions for future, the next exam. And the approaches for solving the reinforcement learning problems with the help of that model are generally termed as model-based approach. Model-based approach, where model is collected or understood for an environment, and then we learn from that. So comparatively, an approach without using a model is generally called a model-free approach. So there are two approaches. One is called a model-based approach, where we have the previous status. So let's say some of the exams we know already. Let's say if we have been going through the program or course, so we knew the past exams, and based on that we can take a decision. But let's say, so that is called a model-based approach. But let's say a new student comes in, that is his first exam or first semester, which means he doesn't know much about the model, what kind of exams will be there, right? So he will be in the model-free approach. It's totally based on trial and error method. And then subsequently, after one or two exams, he will learn and then change his direction, right? Now, let's see how does reinforcement learning work. How does reinforcement learning work? To understand that working process of reinforcement learning, we have to consider two main things. So let's say first the environment. So it could be anything. It could be a room, maze, football ground, or examinations, right? So it could be anything. And agent is an intelligent agent, such as, let's say, a robot. Let's say for an example of a maze environment, an agent which we want to explore. So such as, let's say, this is a maze environment, and a robot has to find a diamond in that. Similarly, you can take an exam center also, such as, let's say, these all are the semesters or maybe separate exams, and we have to reach to the maximum grades, correct? So accordingly, we have to keep changing our strategy. But let's stick to this particular one. So in the image here, you can see the agent is the very first block of a particular maze, and the maze is generally consisting of S6 block, which is a wall. So this is a wall, and S8 block is a fire pit. Right? Is a fire pit, and S4 block is a diamond block, and S4 block is a diamond block. And the agent cannot cross S6 block as it is a solid wall, so it cannot cross. And if an agent reaches S4 block, then he gets a reward because it's a diamond +1. And if it reaches a fire pit, then it gets a penalty -1, right? -1 point. Reward of +1. And if it is reaching at an S4 block, which is a diamond, reward of +1, or if it is reaching S8 block, which is a fire pit, right? So it has to move up, down, left, right. It has to move up, down, left, right. So this is your agent. Let's assume he's here, right? So it has to move up, down, left, and right. It has to move, right? So in that way, it has to go. And it cannot reach a wall because it's a solid block. Cannot reach the fire point or fire pit. It will get a negative reward or penalty. It has to reach the diamond to receive the positive point, right? So now let's see. Now agent has successfully stored the previous steps, and so here it will just keep going. So now let's just go step by step. So the agent will take a particular path. So let's say you can begin from anywhere randomly. You can take it from anywhere randomly. So now let's say agent can take any path to reach the final point, but it has to ensure that it needs to make it in a positive fewer number of steps. It needs to make it positive in a fewer number of steps. Like let's say for example, assume the beginning point is S9 block. Agent is standing here because I wanted to ensure that it is at the farthest point so that it struggles most to reach the diamond and learns maximum. Right? Now, here the optimal path would be S9, then it moves to S5, then it moves to S1, then it moves to S3 and S2, then S3, and then finally it will reach the diamond and accomplish +1 reward point. Agent will try to remember the steps that it has taken, the previous steps which it has taken, and reach the final step. So it will remember all the steps which it takes and reach the final point. And to memorize the steps, it assigns +1 value to each step, right? +1 assigns one value, not +1 value, one particular value to each step, right? So now value equals to 1, then it moves on. Value equals to 1, then it moves on, right? So it gets continue if the value is higher. It gets continue on that path if the value is higher. If the value is not higher, it gets stuck. Now, agent has successfully stored the previous steps. Agent has successfully stored the previous steps, assigning one value to each previous block. So let's say I was standing here, then I assign a particular one value, then I assign a particular one value. It could be, now see, there are different values of them. It could be different also. It could, here in that particular, let's intentionally assume v equals to 1 because we wanted to see what is the disadvantage of that, and then we'll see how we can change. So let's say if the value, I'm standing here, and if I move that direction, value is 1, I'll continue. I move in this direction, value is 1, I'll continue. I'll move in this direction to S2 block. If the value is 1, I'll continue. Then I'll move to S3. If the value is 1, I'll continue, and then finally I'll reach S4. And then finally I'll reach S4. Now, if you look at this, but what if the agent, if he starts moving from the block which has 1 value for both the sides. So let's say if I'm stuck here, I'm standing here. Now if I move towards S2, the value is 1, as well as if I move towards S5, the value is 1. What do I do? See, my correct direction is to move towards S2 to reach the diamond. However, if I compute v equals to 1, which is value equals to 1, in the S5 block, towards S5 block, still I get the same value. So I get confused. So it will be a difficult condition for the agent whether we should go up or down. Right? We should go towards S2 or we should go towards S5. It depends on where it is standing. And each block has the same value, right? Each block has the same value. So this approach is not suitable for the agent to reach the destination based on just marking value equals to 1. Hence, we have to solve this problem differently. We have to have different values, cannot be just one. So we use the Bellman equation. Which is the main concept behind the reinforcement learning. Now, Bellman equation was introduced by that mathematician whose name was Richard Ernest Bellman in the year of 1953. And was associated with the dynamic programming, and he was trying to calculate the values of a decision problem. He was trying to calculate value of a decision problem at a certain point by including the values of the previous states. He was trying to calculate the values of a decision problem at a certain point by including the values of the previous states. Right, which means it stores the previous values which it has taken during the previous actions. Based on that, it calculates the value for the next action. So it is the way to calculate the value functions for dynamic programming, or you can say the environment that leads to the modern reinforcement learning. Now, this was my formula which I have taken from Bellman's equation, which is nothing but Vs equals to maximize the reward for a particular stage by taking that action plus that factor gamma, discount factor, times V of S dash. Here, the key elements of the Bellman equations are, first one is the action performed by the agent, which is referred as A. The next one is the state occurred by performing the action, which is presented as S. So I take particular action and reach a particular state, which is called S. So A is the action taken by the agent. S is the state accomplished after that action. So I take, let's say for example, I study well, that's my current action. If I've studied nicely and then I have reproduced nicely in the exam, then the state is the exam's result. Naturally, it would be better. Now, if the the reward or feedback which is obtained as R during that particular action, and after that state what is the reward. Could be a penalty, could be a reward also, could be a positive, could be negative also. And gamma is nothing but the discount factor. Gamma is nothing but the discount factor. Now this is the Bellman's equation which has been written as, this is the value, the current value, and these are the previous values. These are the previous values associated with the previous actions. Right? Vs dash is nothing but the value associated with the previous state. Right? So here you can see Vs equals to maximize the reward R as A plus gamma times Vs dash. Vs is the value calculated at the particular point. R as A is the reward at a particular point or a particular state by performing a particular action A. Gamma is the discount factor. Vs dash is the value of the previous state. Now in this particular equation, what we are looking, or what we are taking, we are taking the maximum of the complete values, right? Maximum of the complete values, because the agent will try to find out the optimal solution always. Right? So we just take at the, what is the max of the complete values. Now, using this Bellman equation, we will find the value at each state. Using this Bellman equation, we will find the value at each state, and of the given environment, and we will start from the block which is next to the target block. Now if you look at this, let's assume the first block, if I begin, let's say I have been you can begin from anywhere, or let's say the first block can start S3. I'll just start beginning from here. So V value, let's compute for S3 equals to nothing but max R as A plus gamma times Vs dash. Here you can see Vs dash, or maybe we can take a look at the previous block's value is 0, because there is no further state to move, right? There is no further state to move, right? So first block, if you just pick it up, there is no further state to move. That's why it is 0. Now if you take a look, because the next one is straight on, so Vs3 is equals to, let's just step by step calculate max R as A implies nothing but Vs3 equals to maximize of 1. Why? Because here Vs dash, because it becomes 0. So Vs3 is 1. So value is maximized. Why? Because the next one is straight on, I will get a diamond. Right? Next one is straight on, I'll get a diamond. Now if you look at this same calculation for the next, these S2 blocks, the formula is Vs2 equals to max R as A plus gamma times Vs dash. Here, let's assume a discount factor. Because we have discount factor of 0.9, let's assume that. And the previous state's reward was, or the value of the previous state was 1. Here this is my previous state. If I assume this is as a current, S2 is the current one, then the previous state was S3. So Vs dash is equals to 0. Now here, even if I take the action R as A, the reward is 0, because if I go that direction, this direction, anywhere if I go, there is no diamond. Diamond comes only at the end, which means reward is maximum 1 here. So now let's say here, for an example, I was standing at S3, and if I move here, I get the reward which is maximum here, R as A. And this one was 0, because I assume that there is no previous state. Correct? There is no previous state. Now it is in the backward direction. You have to look in that direction, right? So now we can say reward is 1. Now if you look at this, if I am at S2, the previous state is this. I'm just back tracing it. 0.9 is a discount factor, which is here, times the previous state Vs dash, which is 1, and R as A is 0. So reward is 0. Now because see, there is no diamond here, so right, so at S2 whether I move to S3 or at S2 whether I move to S1, there is no diamond, so its reward is 0. Now put just those values there, so this becomes 0 here, gamma becomes 0.9, value of the previous state is 1, so the file value at S2 is 0.9. Now if you look at this, if I am moving away from the diamond, the value is decreasing, so that helps. When I move going towards diamond, the value is increasing, right? So now similarly you compute for the third block, gamma 0.9, reward SA is equals to 0, because if I am standing at S1, that is, and if I move to S2 or S5, there is no reward, so reward is 0. So the value of S1 is nothing but maximized version of 0.9 times the previous value, which is 0.9. So the value of S1 comes as 0.81. Similarly, the value of S5 comes as 0.73. And similarly, the value of S9, which is 0.66. And now if you look at this, our robot, we assume that it is standing at a furthest point, which is block S9. Now we have computed the values for each block. And then we see that if I move from S9 to S5, the value is increased from 0.66 to 0.73. If I move from S5 to S1, the value is increased from 0.7 to 0.81. If I move from S1 to S2, the value is increased from 0.8 to 0.9. If I move from S2 to S3, the value is increased from 0.8 to 1. Right, and then finally we get the reward, and then finally we get the reward. So now that's how we move. Now let's say some of the other points. Let's say now the agent has 3 other options. If I'm standing here, let's say if I'm standing at S7 somehow by mistake, so that's my optimal path for fusing. Let's say now somehow by mistake I reach S7, and if I'm standing here, right? If I'm standing at here, now let's say even if I move towards X6, it's a wall. I cannot do. If I move to S8, it's a fire pit. I cannot do. I get the negative reward. I get the negative reward. Now, what do I do here? So let's say if I move towards that wall, I feel a bump, and if I move towards the fire, I get a negative reward. But here what we have, what we are taking is only the positive rewards, right? So here if you look at this, we have just taken the positive reward, so he will move in the upward direction only. Now the complete block value will be calculated using this formula. So now see what we do here is we continuously compute these values, and then we try to reach the reward point, which is maximized. Try to reach the reward point which is maximized. Now if I look at this, there are different types of reinforcement learning. There are 2 major types of reinforcement learning. One is positive reinforcement learning, and one is the negative reinforcement learning. The positive reinforcement learning, it means that we add something to increase the tendency that the expected behavior would occur again. Which means, let's say, if a model is doing a great job, we give them the reward. So let's say our parents, when we were kids and we were in the school, let's say we were students, and then when we performed good in the exams or some other ways, they gave us some reward, or maybe the chocolate, or maybe cell phone, or whatever you want, right? So it impacts positively on the behavior of the agent, and it will increase the strength of that person, and it will continue that positive behavior. This type of reinforcement learning that can sustain the changes for a longer period of time, but let's say it is over rewarded, then too many rewards, which will again does give diminished return. Could be possible that the system is saturated, and increasing the reward further doesn't give any advantage. The second type of reinforcement learning is negative reinforcement learning. The second type of reinforcement learning is a negative reinforcement learning, where we give the penalty for the negative action. We give the penalty for a negative action so that that reward, so that that state of action doesn't occur repeatedly. In this section, we'll take a look at what is Markov decision process, which is used for reinforcement learning. And let's say, how do we present the state of the agent? We generally present the state of the agent using Markov state that contains all required information based on the historical study, right? Based on the history. Now, let's say the state of or a particular state, which is ST, it would be a Markov state. If it follows the given condition. For an example, let's say P, ST plus 1, under the condition ST is nothing but P, ST plus 1, given all the previous states such as, let's say, S1 to ST. Now, this Markov state follows the Markov property, which says that the future is independent of the past and it can only be defined with the present. The reinforcement learning works on fully observable environment, and where the agent can observe the environment and act for the new state. And to complete the process, the complete process, deciding the states, what would be the next state, is called Markov decision process. So agent generally applies this approach and takes the action so that it will reach the next state. Markov decision process, as we see in the diagram, based on that environment, right? So agent will take a particular action. It will get the reward and it will change the particular state and it will get the positive reward, or could be a negative feedback also, right? Now, Markov decision process, which is often known as MDP, is used to formalize the reinforcement learning problems. If the environment is completely observable, then its dynamic can be modeled as a Markov process. If we are able to observe the environment, we can model that as a Markov process. And in MDP, we constantly interact with the environment. The agent constantly interacts with the environment and performs the actions. And the environment responds and generates each action. For each action, that environment will respond with a positive feedback or positive reward or a negative feedback and generates a new state. So let's say I am looking into the environment, I'm studying for the exam. Let's say I got good grades, correct? That is a positive reward. I'll continue and study more. If I'm not getting good grades, right, I have to change my strategy, observe the rewards and study more with a hyper focus. So MDP is generally used to describe the environment of the reinforcement learning, and almost all the reinforcement learning problems, they can be formalized using MDP. Now, MDP contains a tuple of 4 elements. Where S represents states, A represents actions, A represents rewards which have been received when we move or transit from state S to S dash, and PA is nothing but the probability, right? Because generally we calculate the probabilities and MDP uses the Markov property. So let's say it says that if an agent is present in the current state S1, assume, it performs a particular action A1 and moves to the next state ST. Then the state transition from S1 to S2, it depends only on the current state and the future action, and the states do not depend on the past actions and the rewards or state. That is the Markov property. That is the Markov property. So let's say if I am at S1, I take a particular action A1 and I reach S2. The transition from S1 to S2, it depends only on the current state and future action. It depends only on the current state and future action. And the states do not depend on the past rewards or the states, because what it tries to say that everything is being materialized in the current state. So let's say my grades are good in the current semester, after the current semester is over. That means all the past actions have been materialized and quantified in terms of the grades of the outcome. Right? Now, the future state depends on the current state and how I will prepare for the next exam, right? Now, it doesn't depend on the past actions that have been taken. So now, based on the current actions, which I am right now in the current state, the future depends on. Or in the other words, as per the Markov property, the current state transition does not depend on any past action or state. That is the Markov property. Hence, MDP is an RL problem that satisfies the Markov property, such as, let's say, chess game, or the player only focus on the current state and do not need to remember the past action. So let's say you are playing for the cricket, right? So what we focus on the current ball, how it comes, or you are playing the football. So it just depends on the current play strategy, that how it is coming up, right? So that's the Markov property. Markov MDPs could be two types. One is like the finite MDP. MDP is like finite MDP. If you look at this finite MDP, is when we have the finite states, finite rewards, finite actions. Everything is finite, right? Everything could be defined finitely. That is called finite MDP. And mostly in RL, we consider finite MDPs. The Markov process, right? So the Markov process is generally is a memoryless process, right? With a sequence of random states such as, let's say, S1, S2, so on up to ST, which satisfies the Markov property, which uses the Markov property. And the Markov process is also known as Markov chain, which is a tuple, what we have just seen, And the major components we had just seen that on the previous slides. The next type is a Q learning. If you look at this, Q learning is an off policy of the RL algorithm, which is generally used for the temporal difference based learning. And the temporal difference learning methods are the way for comparing temporally successive predictions. It learns the values of the Q function, which is nothing but Q, state and action, which means how good that action was taken and how for that reaching that particular state. Now, if you look at this, first what we do is we try to initialize the Q table, then select the action to perform that particular action, keep an eye on the reward, measure it, and put it in the Q table, update. Then you again go, select the action to perform, calculate the Q value, put it in the table, and create a Q table, right? To do that, we often use state action rewards, state action, reward state action. This is called SARSA algorithm, state action, reward state action. So SARSA stands for state action, reward state action, which means is an on-policy temporal difference learning method. Where we have seen that the off-policy, which is nothing but Q learning, this is another one, SARSA. It is on-policy temporal difference learning method. The on-policy control method selects a particular action for which the state, while learning using a specific policy. right? And the goal of the SARSA method is to calculate the Q values or Q based on a particular policy, the selected policy, which you can say pi as A, or you can give any name for that pairs of state and action. So let's say I have a particular policy, I took a particular action to reach a particular state. Calculate the Q value, put it in. Now the major difference between Q learning and SARSA learning is, unlike in Q learning, the maximum reward for the next state is not required for updating the Q value in the table. That is the difference here. Whereas in Q learning, we used to compute the maximum reward. Here what we do not compute the maximum reward, but we look at the optimal policy which may try to maximize the reward. So it's kind of a policy based. SARSA is a new in SARSA algorithm, the new action and reward are selected using the same policy. The new action and rewards are selected using the same policy which has been determined in the original action. Now if you look at this, SARSA is named because because of this Q as A or S dash A dash, right? Here you can see the major component. S is nothing but the original state. A is nothing but the original action. R is the reward observed while following the states, and then S dash and A dash is nothing but a new state and a new action which is taken for a particular reaching that particular state. So it's a transition from the previous state to a new state. So S dash, A dash is a state action pair. There is another method which is called deep Q neural network method, DQN, which is called deep Q neural network, DQN. As the name suggests, that DQN is a Q learning using the neural networks. Now, for an example, let's say for a big state space environment, it would be really challenging and it would be a complex task to define and update the Q table very frequently and maintain it. There are too many states. We cannot handle it manually. To solve this kind of issue, what we do is we can use the DQN algorithm to solve this issue. We can do that. What we can do is we can use the DQN algorithm, where instead of defining a Q table, the neural network approximates the Q values for each action and state. The neural network approximates the Q values for each action and state, and then it will update. So we use the Q for manual operation of the Q table. Instead of that, we use the neural network to approximate the states and action and then update the Q table. Q learning is a very popular model-free reinforcement learning algorithm. Very popular model-free. Q learning is very popular model-free reinforcement algorithm based on the Bellman equation. And the main objective of the Q learning is to learn the policy which can inform the agent that what action has to be taken in the direction of maximizing the reward under those circumstances. And Q learning, if I summarize, then it was an off-policy reinforcement learning that attempts to find out the best action which has to be taken at a current state, and the goal was that the agent in Q learning has to maximize the Q value. And the Q learning, generally it has been derived from the Bellman equation only using this particular formula. We can say that value of that particular state is nothing but in such way so that the reward generated through the state has to be maximized, plus gamma, which is nothing but a discount factor. Take the summation across the previous states and the penalties of that particular action or reward, and then what are the values of the previous state. So now see, this is again a derived version of the equation from the Bellman's equation, which you can further refer. And applying that equation, what we do is we can keep calculating the value functions, or let's say we can use the MDP also and then keep calculating them, and then we keep updating that table and reach that particular thing, right? So let's say here Q represents the quality of the action which we have taken, right? So let's assume that a robot is standing here, right? So if it moves here, the quality of the action taken by that particular action A1 reaching that state as 0. I mean from moving from here to here, that is the next one, and then or maybe as 0, it was standing there, what is the action taken to reach here? Then you move in that direction, what is the quality of the action? Move in that direction, what is the quality of action? And so on. And try to maximize the value. Try to maximize the value of the reward, right? Try to maximize the value of the reward. That's how the Q learning method works, right? Here Q stands for the quality in Q learning, which means it specifies the quality of the action taken by that particular agent, and my job is to maximize my quality of the action in such a way so that the reward is maximum. And then finally, the Q table is nothing but a matrix or a table that is created while performing the Q learning. And the table follows the state and action pair. It registers a particular state and action, and it initializes generally when it starts, it initializes as 0. And after each action, table is updated, and the Q value are stored within that particular table, and Q values are stored within that particular table, right? And the reinforcement learning agent that uses this Q table as a reference table to take the best action of the Q values. So let's say if I'm a student and I'm studying, right? Let's say my course could be a 10 semester or 8 semesters course, then I have a table. Let's say semester 1, the performance index is 8. Semester 2, the performance index is 7. Semester 3, the performance index is 9, and so on. That is a table, right? And based on those entries in the table, I can change my action in such a way so that I can increase my performance index. So that table is useful. Let's take a look at the differences between the reinforcement learning and supervised learning. Let's take a look at the differences between reinforcement learning and supervised learning. Reinforcement learning works by interacting with the environment. Whereas supervised learning works based on the existing datasets. Supervised learning works based on the existing datasets. The reinforcement learning algorithms, they work like a human brain, right? Like a human brain, by making the decisions, trying, failing, succeeding, and supervised learning works as when a human learns the thing under the supervision of a guide. Let's say supervised learning, we need a supervision, and under the supervision it has to work. So for example, let's say we attend an exam under the supervision of a particular instructor, and then we attend the exam. That is called under the supervised we do. Or let's say we are working under the supervision of someone, and then he supervises and we learn according to that. Whereas reinforcement learning is kind of explore, learn at your own through your mistakes, change the direction based on the reward or penalty. There are no label data set, or there is no label data set is been present in reinforcement learning. Whereas in supervised learning, we use the label data set. No previous training is provided to the learning agent. It's kind of a training on the job. No previous training is being provided. Learn at your own, explore at your own. Whereas in supervised learning, we provide the intense training to the algorithm so that it can predict the output. Reinforcement learning helps to take the decision sequentially. It's kind of a sequential decision, right? One decision you take, measure the action, then the next decision. One decision is taken, measure the action, and then the next decision. In supervised learning, the decisions are made when the input is given. Right? So when we have given the input, based on the training, supervised learning will just make a prediction and say, based on my previous training, this is the output prediction. There are certain applications of the reinforcement learning. We are moving towards the end of the session now, such as, let's say, reinforcement learning is being applied in healthcare, education, transportation, energy, business management, engineering, natural language processing, computer vision, robotics, games, computer system finance, right? There are many places where reinforcement learning have been applied. That's all we have for today's session. Thank you very much for your time and patience and listening to this session.